Okay, this video will be using the SRP table to try to predict spontaneity. We're trying to answer the question, will this species be able to oxidize this other species, or will this species be able to reduce this other species? So what we're going to find is, we'll go into that in a minute, but here's a little bit of background stuff that's going to help us out here. So these up here, way up here, these are the best oxidizing agents, which means they're very good at being reduced, these up here. And when I say these, I'm referring specifically to the reactant side. And we'll notice that these are mostly non-metals on the periodic table. The flip side of that are the species down below at the very bottom of this table. As we see, the reduction half reaction gives off a negative voltage. So that means if we reverse these, they happen very readily. So these are the best reducing agents, meaning these over here on the product side are easily oxidized. So, and this is true because we know that we have some group 2s and group 1 metals, and we know that these guys, these metals, these don't, or these actually give off their electrons readily. So if we write these in so if we write these in reverse, then we flip these signs, then we get positive cell voltages. Another way to say that is on this next slide here is that up here, these really like electrons. And when I say these again, I'm referring to the reactant side over here. So F2. So if I try to flip this and write it like F minus is losing electrons, then we see that we change the side here. So this guy really wants to keep its electrons. Okay, so that's another way to say it. And then over here, these metals on the product side, these metals right here, they do not like electrons, so they are easily oxidized and they lose them readily. Okay, so let's use some of this information and try to apply it to some questions here. So first of all, here's the first question. So is K plus a good reducing agent? So we need to translate this vocabulary here, and then we're gonna ask: is this good at being oxidized? So that's the first question we can ask. So it's asking: is K plus a good reducing agent? So is K plus able? Is it good at being oxidized? And what does oxidize mean? Oxidize is loss, or loss of electrons is oxidized. So is K plus able to lose electrons? So you see that once we translate this vocabulary into a usable term, then we're going to see that this is actually a ridiculous statement. So because we're trying to figure out, does K plus do this? Okay, does it get oxidized easily? So if it gets oxidized, then it'll make a K2 plus another electron. And as we know, potassium, once it loses that one valence, we start pulling from the core, which is really, really hard to do. So this is really, really bad at being reduced. Really bad at being a reducing agent. Okay, so it's really bad at being oxidized. It's so bad that we never even see this. This actually looks really, really strange. So we'd actually never encounter that. So we need to translate this vocabulary into some usable terms here. So this is so bad, in fact. I mean, this doesn't even appear on our SRP table. So let's ask another question about potassium and the potassium ion. Okay, is K plus a good oxidizing agent? Okay, so let's translate this vocabulary. So we could phrase this a couple different ways. So is K plus good at being reduced. So does K plus accept electrons and make solid potassium? So if we have a 1 plus and we accept electrons, then it will no longer have the charge. So it gets reduced from a plus 1 to a 0 charge. So is this good? Does that happen easily? So is let's continue trying to translate this and put it in different words. So is K plus good at accepting electrons? So we can look at our SRP table here, and we see that let's take a look and see how how well it does at the potassium ion. Let's see how well it does at accepting electrons. So here's potassium here, the potassium ion, and we see that it's actually terrible, quite terrible at accepting electrons. So it's a negative 2.92. So this is also it's not as ridiculous as the question before. At least it appears on the SRP table. But this is the half reaction of K plus being reduced or acting like an oxidizing agent is very bad. So the reduction half reaction for this is negative 2.92 volts. So this is horrible. The K plus ion is horrible at getting reduced. Okay, so let's take a look at another question, and now we put it in the solid form. Is this a good reducing agent? So let's translate this again. So is K plus, or I'm sorry, is K solid potassium good? So a reducing agent is one that gets oxidized, and then we go, and then our mind goes. So we translate that first, and then we could think of oil or Leo. Okay, so is it good at losing electrons? Losing electrons. So is K plus good at losing electrons? So let's write that half reaction. Is it good at getting oxidized? So an oxidation has it going from a 0 to a plus one electron. Okay, and if we pull up this, it's actually the reverse of this reaction. Okay, so it's actually number 56, but the reverse. So we need to flip this sign and we get a positive 2.92. So we have E ox is equal to a positive 2.92. So written this way, we show the solid potassium losing electrons, and then we get a positive half reaction. So yes, this is very good reducing agent, one of the best. Yes, solid potassium is a very good reducing agent. Okay, so um, let's look at a question here. So let's go ahead and try this question. So we're going to try to predict how well these are at uh, their oxidizing agent strength. So we're trying to figure out are these easily or let's take a step back. So increasing strength as oxidizing agents. So it says place these in order of increasing strength as oxidizing agents. So we want to put them from the least easily reduced to the most, or we could rephrase that. So the hardest to reduce to the most to the easiest to reduce. So let's take a look and find these on our SRP table, and then we'll write the voltages underneath. So I'm going to write little half reactions under each one of these. Okay, and let's take a look at, so we need to look for these on the reactant side. So we need to find Cd2 plus some electrons making solid cadmium, um, the iodate ion plus some electrons. I believe this one happens in acid and water, and it's a pretty long half reaction. So K plus electrons, H2O plus electrons, um, this gold chloride ion plus electrons, and the I2 plus electrons. So if we look at our table, so CD2 plus is reaction number 42. So it'd be this one here, CD2 plus. So we have a negative zero point 0.40. So this one is negative zero point 0.40. This one, so this was reaction 42. This one, if we look it up on here, we have IO3, which is reaction number 16. So it's this one here, reaction 16. And we have 1.20. So we have a positive 1.20. This was number 16. K plus, this one's down at the bottom. It's reaction number 56. So this one's negative 2.92. The H2O. Now this one's kind of interesting because you'll see a lot of waters on the SRP table, but those are just reactions that need to happen in an aqueous environment. So we want to find the one that just has water and electrons on the left. So let's go ahead and check this out. So it happens to be number 47. So just electrons and water on this side. So there it is, this one. So you'll find that there's a lot that have water. Okay. Actually, there's quite a few that have it water on the right side. That looks like one of the only ones with it actually on the reactant side. So this is the one we're looking for. So that's a negative zero point 0.83 for this one. Negative zero point 0.83. That was number 47. This one is number 19. This reaction, it's a plus zero point 0.99. And then this reaction is number 28, which is a plus 0.54. So the hardest to reduce are going to be the ones with the highest negative values. So K plus is the hardest to reduce. So that's the worst oxidizing agent on here. As we see on our intro, on the introduction, K plus is or it's actually it's solid K. That one is a good reducing agent. So K plus, this one is better than, or H2O is a little bit better than that one. And then CD2 plus, so I'm just going in order of the voltages. Then we have I2. Then sorry. Okay, then we have I2. Then we have AuCl4. And then finally we have IO3 minus 1. Okay, so this is the correct order for, we put them in order of increasing strength as oxidizing agents. Okay, so here is the practice one for you to do, and this one says to put these. Let me give you a couple little hints here. So this one says to rank these in increasing strength as reducing agents. So on the example I did, I put them in order of increasing oxidizing agents. So this one's a little bit more tricky. So we need to look for these, all the ones listed here on the product side. Okay, so let me do so you're gonna actually reverse all of these. So I'll do like these two, the first two, just to get you started, because it is a little bit different than the example I did. So Mg, we want to see how good these are at being oxidized. So we want to write Mg going like this, Mg2 plus some electrons. So these are going to be on the reactant side. And if we look at our reduction potential table, we see that that reaction is this one here. So these, it's actually the reverse of this one. So we're going to reverse this sign right here. So it's the reverse of number 51. Okay, and the voltage, so we're going to change the sign on all of these. So reverse all of them. So reverse all of them and then flip the reduction potential to get, so flip it to get the oxidation half reaction. Okay, and remember, so write these out. So it's so we're looking at I minus being oxidized to I2 plus some electrons. Okay, or chromium being oxidized to, I think it's a 2 plus. Okay, so we're going to look for those on the reactant side and then flip the sign. Okay, and then see what you guys can come up with on this one. That's the end of our tutorial.